We'll now look at different approaches to updating the weights within an epoch. The approach we described so far is called full batch update. The entire training set is used to compute the gradient and update the model's weights all in a single step. This means that for each epoch there is only one weight update. This tries to correct the error at all of these training data points, all at the same time. The advantage of this method is that it provides a clear and stable path towards minimizing the loss, as it's less susceptible to the noisy gradients that can occur with smaller sample sizes. However, the downside is its inefficiency with larger data sets. Processing the entire dataset can be computationally intensive and slow, especially when using deep neural networks or when the dataset is very large and has millions or billions of data points. Moreover, full batch updates might not be feasible if the dataset cannot fit in memory. The opposite approach is called incremental update. Here we will adjust the network parameters after processing each individual training example. This means that each individual update to the network will be smaller, except now instead of making just a single update after processing all training points, we would have made many updates to the function within a training epoch, one after each example. With incremental updates, we don't want to process all data instances in the same order for every epoch, as this can sometimes lead to repetitive patterns in updates that could cancel each other. To avoid this, we shuffle our data and pick instances randomly. This method of random selection and update helps prevent cyclic update patterns and is known as stochastic gradient descent, with stochastic referring to the random selection of training instances. The frequent updates of stochastic gradient descent introduce a lot of noise into the learning process, which means it may take longer to converge to a solution and the path to convergence can appear erratic. On the upside, stochastic gradient descent often leads to more robust solutions. Mini-batch gradient descent strikes a balance between full batch and incremental updates. Instead of using the entire dataset or a single instance, mini-batch updates use a subset of training data to compute the gradient and update the weights. The size of this subset, the mini-batch, can vary, but common sizes include 32, 64 or 128 samples. This approach combines the computational efficiency benefits of SGD with the stability of full batch updates. The average gradient across a mini batch tends to be less noisy than SGD, leading to more stable convergence, while still being computationally efficient and able to benefit from parallel processing capabilities of modern hardware such as GPUs. This was a quick take from LLM Chronicles. If you enjoyed this snippet and want to dive deeper into the world of deep learning and large language models, just check the full episode in the description below. Don't forget to like and subscribe to support the channel and get notified of all new content.